ahead and get started. A little bit late here. Problem, I left my recharger in here last Friday. I have not returned the camera. It's going to crap out. It tells me it's going to make it about 40 minutes. Sorry about that. So today's lecture will be cut short on video. Not that I'm going to cut it short because I have stuff to go with your exams on Friday. But, sorry, sounds. So you don't have much to say with your stuff here. Again, so the video will cut out a little bit early. Sorry about that. I just forgot and left it in here. Oops. Won't have it again. Let's see. You have a homework due Wednesday. Remember, I'm not going to assign another one because that's too much work for me and the TAs. Because then we have a test on Friday. I worked the test over the weekend, and it's relatively easy. And I think very carefully about like what I've said in class and what I think your strengths and weaknesses are. So remember, if you're looking at old tests, for one, there's been a major curriculum change. So if you're looking at old tests, you're just screwed, because that's just not the test. So I would not recommend doing that. You will answer the questions on the old test if that's what you have. And I've said that many times. I know I'm a broken record. The present homework, if you haven't looked at it yet, you're screwed. You need to go ahead and start on it today. It's one of the longer, harder ones. So if you haven't started on the homework, do so right now. Let's see, now one of you mentioned on one question, which one was it, number 3 or 4? I asked for VI, and I really meant to ask for VF. Which one was it?
Yeah, it was both 3 and 4.
3 and 4, now let's see, now one of them was right, the other was wrong. Don't worry about it, you know what I'm going to do? I'm just going to cut it off the key. You have to figure it out anyway. So I'm just going to cut it out of the key so the grader will grade it. But you have to calculate it anyway. It's not a big deal. It doesn't change anything. So, slight mistake. Sorry about that. And remember, so what to tell you? I am going to lecture. So Wednesday we have the review stuff. 2 questions on the test come from today's lecture. Just write it down, right? So I'll point it out to you. Wednesday again is the review, and you know I will lead. Well, you're learning. I'm going to bleed like a fish. I'm going to tell you almost everything on the test, because I tend to do that. It doesn't even really matter if I do or I don't, in all honesty. Just like I give you the answers to all the questions. I actually have not done that as much as I do on the homeworks, because I mean, as you've noticed, I give you nearly half the answers on the homeworks. I haven't done that so much on the test, but there are answers to questions embedded in other questions. Only about 2 or 3 instances of that. So, just what I did. I have three more questions to write, so I'm still working on it. So, we okay? Anybody have any questions? We're doing all right. So, okay, no questions. Want to just review that we started talking about heat over temperature. And heat over temperature ended up being exact by Euler's criteria. And if it's exact, it has to be a state variable. And of course, as the engineers already know, because we've had this for the 3rd time, that it's actually related to the change in entropy. I'm getting there. All right, but today we're going to talk about entropy. Has so many different facets. We're going to talk about one of them now for the next 2 days, actually. And then we're going to go over the other facet of the exact same thing. And they're not going to seem like they're related at all, but they are. It's very, very strange. So now I'm introducing entropy as I introduced before, as that thing that you can't do, which is to turn all heat into work. And this is the bane of our civilization. So I represented that this way. And this is work, and then this is heat. So you can't turn all heat into work. Anyway, it's a very traditional way of showing this, so I don't really care. It's not on the test. I'll tell you what's on the test. What's on the test? Let's see. I'll tell you a little bit what I'm doing today. Okay. So you can't turn all heat to work, so how much heat can you turn to work? And that was actually figured out by that guy, Carnot. I told you about him last time. I know when I was walking along with the boring detail of Carnot in his life, or his latter life, because he was relatively young, 34, and he had figured all of this out when he was building cannons. But he was right. He didn't even know what entropy was. Entropy isn't really part of the Carnot cycle, but it does play a part. Now here's the thing. Get a whole piece of paper for this next bit. This part is painful. Okay. Now I kind of hate today. Every time I do this, it's really kind of painful. I have to draw this big, huge diagram. and it's going to take forever to go through it all. Anyway, but part of this is on the test. Okay, so what we're going to do is, now remember, this is all about a reciprocating engine, right? This kind of engine. Because spring engines suck. You just don't go very far with that. You can also use, you can use compressed air as an engine. But again, it only goes so far and then you're done. A reciprocating engine can technically last forever. That's what Carnot figured out, and that's exactly how we build everything. That's how your cars work, and how your car works, how the power plant works. We've never come up with something better. 200 years ago, we figured all this out, and we have not come up with anything remotely better. Except there's this one idea of using the tides as a form of fuel, wind power. Those don't work, in all honesty. If you look at wind power, renewable energy, it's all about 1% of what we get by burning coal and gas. So it's a drop in the bucket. It's just not going to do anything. So that sucks, but that's reality. So anyway, all right, so reciprocating engine, got to go forward and backward. All right, so what we're going to do is start with P1, B1, and T, what am I going to call this? Let's screw this up every time. P hot. Sorry, I make a lot of mistakes when I do this. I tend to screw this up, by the way, so just forewarned, all right? It's a lot. Sorry about that. Okay, so we're going to expand hot. And we're going to come to a stop at some point, like in your homework, which are your numbers, and we're going to be at P2, B2, and we're still going to be hot. Okay. Now here's something I forgot to go over, and I'm really sorry about this. I do this every year. Now I mentioned that we're going to have to cool the engine, right? So we expanded the gas while it was hot. We did that by burning gas. And then we're going to open a magic valve. The magic valve goes to the tailpipe. The tailpipe's cold, so it's going to magically cool the gas. But instead of magically doing it, we're going to do it adiabatically. And this is the part I forget. So when it comes to, all right, so these are isotherms, right? But when you are doing it, so isotherm, right? Constant temperature. Now I'm lowering temperature, and that makes this an adiabat. Adiabat isotherm. What makes it an adiabat? I said number 2. The other thing I keep forgetting. Remember, if I'm going to expand adiabatically, I'm going to cool the gas. So I'm going to, let's see, I'm going to expand. That's going to lower pressure, but I'm simultaneously lowering temperature. Now, that's across the aisle from P. That's going to lower P more than if you did it isothermally. So, adiabats slope harder. That's my term. It's a harder slope than an isotherm. And I keep forgetting to point that out. Every freaking year I get this where I'm like, uh-oh, I haven't explained this. Oops, oh well. Well, that's the worst mistake I ever made. It's not so bad. And then, of course, we're gonna be cold now. Now we have to do the reciprocation. We've been expanding, which is negative work, and that's good. All right, that's this part, which makes sense. All right, now we have to go back. And again, I don't ever draw this very well. I'm doing my best. And let's say we go here, and that's going to be P4, B4, and I'm still cold. Still a cold temperature. And then I have to raise the temperature back up for the expansion. Now again, normally I burn gas to do that, but I'm not going to do that in this hypothetical magic engine. Instead, I'm going to adiabatically compress. There you go, an adiabatic compression. All right, so again, what's special about this? We're going to cover it. I know it's all like, so what? You're going to see in a minute. This is the best engine. This is the answer to one of the questions on the test, by the way. Right. This is the best engine. This is the most efficient engine you can build. When Carnot figured out to do things this way, which we have there are little model toys that actually will follow Carnot cycles as best as a human can build. It's the most efficient engine possible, but it's not totally efficient. But you can't beat it, right? So that's kind of important. So anyway, I'll even explain the things about airplanes actually shortly, because airplanes actually work on Carnot cycles as well. But I'm getting there. Anyway, I'm winning my mouth. Okay, let's do every leg. Now this is where this is painful. I've got to calculate the heat and work of every freaking step. So this is why I put this on kind of a big thing, because it takes a while. Okay, now your engineers have been blasting me for forgetting to do this. I'm doing it correctly, so if you appreciate it. I keep putting little delta as opposed to big delta. I thought you were less OCD than me. Okay, if I'm adiabatic, isothermal, then this is the case. And I know my equation for reversible isothermal work. I know that formula off the top of my head. I don't even have to think about it. nRT hot. So the natural log of V2 over V1. Is that right? Of course it has to be that. Okay. LNDF over VI. There we go. Okay, so that's that. That's easy. Okay, let's do the next one. I'm going to forget my units. That one's easy. And remember, it's adiabatic, so when I say isothermal and I have this on the test, you instantly write down delta T is 0. When I say adiabatic, you write this down. Instant points. Okay, and the change in work is kind of undefinable. Instead, I'm going to calculate it as though it's a change in U. That's also on the test. And remember that little diagram I once drew about adiabatic expansion, and I showed you how you could break it up into two different legs because you're going to need to do it on the test. And from what I got from that was CV delta T, and that's going to be T cold. Don't let me screw this up. T cold minus T hot. There you go. Okay. Halfway through. Let's do the rest. Okay. This guy. The third. Here. Let me make this easier. 2. Sorry about that. EQ3 is minus the change. No. Sorry, that's better. Is that how I did it? I think that's how I did it, yep. Okay, this is minus nRT cold, natural log, and that's going to be V4 over V3. Okay, so that's heat and work, and I think that's about it. And then this guy, again, adiabatic compression. We'll have no heat transaction, right? Remember, its purpose is to get hot so we can expand, and the work, and that's number 4, right? And that is CV, I'm sorry about this, T hot minus T cold. Sorry about this. Usually I don't screw this up, I just screwed up. Anyway, there you go. So, sorry if your diagram's a bit of a mess. This is the best I could do. God, this is ugly. I hate doing this every year. Every year it's a bloody awful mess. So, not a lot I can do about it. Okay, now here's the general idea. I'm going to try to add up the work. And as I badly screwed up last time when I was talking about Joule-Thomson, I had this note for 8 years, and I can't believe my notes are screwed up. And no one is cut except you. That means you guys are doing great. So, then I do expect a really, really high average on the test. Normally the first test usually doesn't go so well because you're still trying to figure it out, trying to figure me out, which is bad, but what can I do? I'm the only guy here available to teach the class. But you guys seem to be doing much better, so am I still talking? What am I talking about? I don't even remember. Okay, here's the general idea. I'm going to add up the work, and then I'm going to think actually in a peculiar way about heat. And knowing that I drive the car by burning gas, I'm going to calculate the heat over the work. And that's going to be the efficiency. If it was 1, that means all the heat got turned into work. But that's impossible. That's impossible. But how much heat can you turn into work? Well, we're going to calculate that. And this is what Carnot figured out, that he was building his cannons, didn't have a car. Okay, let's do the total work. And how about I switch boards? Here we go. Let's see. So I'm just going to add this sucker up. Total. I don't remember what the heck I was trying to bring up. I was trying to bring up the fact that when I was doing the Joule-Thomson, I mentioned how, what did I screw up? I screwed up because I said U2 minus V1. Actually, that ended up actually being correct anyway. But what I really needed to do is to sum the total change. And again, changes can be positive or negative. Just let them be what they want to be. But add them together. Energies add together. They're all different. Okay, the total work is, okay, kind of painful, nRT hot, natural log V2 over V1. Sorry, I seem to be going very slowly. Plus, okay, a little bit of a reminder. I don't want you forgetting this, that when I give you a heat capacity, I'm going to give you a per molar heat capacity because that's how I find it on the internet. So you got to multiply it by moles. That's going to be T cold. Right, final minus initial, that's right, T hot. Okay, and then I'm going to add in a negative because IUPAC decides that this has to be negative. It's going to be cold. Natural log, and that's going to be V3 over V4, right, V4 over V3. Does that? Yeah, okay, that's good, that's good. And then add in, see, I almost put up NCV mole, T hot, minus T cold. Okay, there you go, not bad, not bad. All right, I can eliminate two terms.
CV terms. CV terms.
1, 2, 3, 4, which terms?
CV terms.
Right, the CV terms. Yeah, here you go. Cold, hot, hot, cold. Same, minus. There you go. Okay, so, then what do I do next? Let me just make sure. Okay, yeah, I'll just write it down just for the hell of it. T hot, log V2 over V1, minus nRT cold. Sorry, that was weird, doesn't it? I don't know why I did that. Natural log V4 over V3. Okay, so what? Well, it turns out that, those adiabats. Those adiabats are really kind of identical. And if they're identical, then I simply ought to be able to connect V2 to V3 and V4 to V1. It kind of makes sense. I should be able to do that, and I can. And what connects them is ultimately V2 to V3 undergoes a change in temperature, which is equal and opposite of V4 to V1. It makes sense. I should be able to connect them. I just have to figure out how. That's the next step. All right, how do I do that? Okay, so, oh my God, this is horrible. I hate it when I have to write a whole equation across the board. It drives me nuts, I'm sure it drives you guys nuts. Okay, so if VI over VF is TF over TI, the CV over NR. If this is true, which it is, therefore, V2 over V3, yeah, 2 to 3 is where we have a change in temperature. And let's see, the final temperature is the cold. What have I done? Yeah, that's T cold over T hot. Sorry. Leave my own notes there for a second. Over to the CV over NR. Okay. And V4 over V1. Okay, so that's right, initial. I start at V4 and I go to V1, and that's going to be the opposite. T cold over T hot. So CV over NR. There we go. All right, you got that down. It's not hard. And that means that, how do I want to do this? V1 over V4. Looks like I painted myself into a corner. Okay, I painted myself into a corner. What I'm going to do is flip these guys. T hot over T cold. CV over NR, which is now V3 over V2. Right. Cold over let's move it up.
Should be T hot over T cold, right?
Final is hot. Right. Final is the hot. What? Yeah. Yeah, I mean, this is, let me double check. All right, I know it's right. Yeah, that's right. Sorry about that. I go on automatic and I screw things up. And so therefore now, sorry about that. I try not to make stupid mistakes, but it happens. So let me T cold with T hot. All right, here's too terrible. It's just going to be 2 over V3. Okay. And what does that give me? That means that, again, because I'm doing a pretty good job of screwing up, V4 over V3, V4 over V3. Okay, bring this over here. Oh, sorry, I know this looks awful. 4 over V3 is V1 over V2. Okay, again, doing a derivation, then I do another derivation, I go back to the derivation. So, V4 over V3 is V1 over V2. nRT hot, delta V2 over V1. Okay, so obviously I can sub in V1 over V2, or I could bite the minus sign, so I'm doing 2 steps at once, V2 over V1. Right, I'm biting the minus sign by doing an inversion, right? ln minus ln A is ln to the minus A. A to the minus 1, anyway, sorry. Flipped it, brought myself a negative sign. Negative, negative, positive, there we go. Okay, what's the total work? Okay, it's minus 1 of u, yes. nR ln V2 over V1 times T hot minus T cold. Hopefully my handwriting's not too terrible. Okay, very good. Thank you everyone for putting up with me. All right, let's see here. Hot minus cold, positive, negative.
Positive.
Positive, of course, positive. Positive, V2 greater than V1, natural log of a number greater than 1 is positive. Positive, 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 positive. But then I got a negative. Take you IU hack. All right, so that means that one thing I got out of this is that the total work in this system is ultimately negative. And again, I can't emphasize this enough. It's just a practical thing that chemical reactions tend to get hot. They don't tend to get cold. And so that makes a very simple way to make hot gas. It's much easier to make hot gas than cold liquid. Or that would be the opposite. We like to take cold liquid, turn it into hot gas, not the other way around. There are reactions that will go from hot gas to cold liquid, but they're few and far between, and they're not very efficient. They're not very fast either. But burning gasoline is really, really freaking fast. So we like to expand hot things, and if I'm going to expand, well, there's my power cycle. Then valve opens the tailpipe, and then we compress when we're cold. Doesn't work super great, but it works as well as anything else we've ever come up with. So, net negatives work, power struggle. So that's why that happens the way it does. Okay, now, this is the part that gets kind of painful. Let's do the heat, and I'm going to have to erase my Carnot cycle. I don't really have much erasing on this.
Before you actually erase it, just wondering for the last, for part 3, is it negative nRT also?
I'm sorry,
Delta Q3, is it also negative?
yeah, you're having trouble saying it, so, because I'm not writing it very well, that's my fault. Minus, definitely minus, yeah. Yeah, I know, it's never goes that well. Thanks for pointing it out, though. Hopefully the video is a little bit more clear, especially if I screw up or you're having trouble seeing something. And by the way, I'm going to put this on my handout because it's a little bit too much, it's a little overwhelming. And one thing I've noticed is that sometimes, even if I get it right, sometimes you don't. Not that you're stupid or anything, it's just that there's a lot of stuff here, and you're missing a minus sign, you're missing a factor of 2, and then it doesn't work. So anyway, so I do have this all written up in the handout. Okay, so let's do the heat. Okay, delta Q1 is minus the change in work, 1. And our heat hot, natural log V2 over V1. Now let's see, that is going to be, let's see, V2 over V1. Right, so I have that minus sign V up here. All right, so V2 over V1 is positive. The rest of it's positive, so this is a positive heat. This is heat into the system. And with delta Q2, delta Q4 is 0. Again, I'll give it units because I'm supposed to. And then delta Q3. I'm already just writing what's already, well, actually what I just deleted. So I guess I do need to write this. nRT cold, natural log V4 over V3, which would actually be negative, but I don't care. Okay, funky thing. No, I'm not going to start dancing. That would be funky. All right, I want to think about, again, I had to inject heat into the system. I had to inject heat to get to the power stroke. The compression stroke, I don't care about. That's just the flywheel, that's the thing's momentum, right? So I don't have to do anything about this. It kind of does it on its own. Again, this part is going to happen by simply sheer momentum of, remember that, the flywheel. All right, this part I have to do. This is me igniting the gasoline. This is why I had to pay money to drive the car. I had to fill it full of gas. The gas has to get a spark. Ooh, that's nasty. Very OCD today. The gas needs a spark. The spark needs to burn the gas. The gas needs to get hot. And that's exactly what this step is doing, not this step. I don't have to do anything to make this happen, other than get some Germans to build a car. This part is the part I have to pay into. So this part is where energy comes from me, and that's all that I care about. So this is the heat that I had to put in, and if I divide it by that amount of work, then I know how efficient my car is. Okay, another damn thing. We like to not say work is negative. We just don't like negative things. I don't know why, but that's just how it is. So what we like to do is define efficiency. I never know what my spelling is going to do. As, let's see, the absolute value, oh, I think I told you this wrong. Sorry. Yeah, I told you this wrong. I got this screwed up. Sorry, there's no work, there's only changes in work, and then there's the heat that I added. Okay, again, the absolute value on the work is just because I don't want to report a negative efficiency. It's meaningless. It's just I don't want to put a negative number. All right, and then this guy is not this plus that, it's just that. So all the reasons I've been blabbering about for the last 10 minutes. Okay, let's do this. Okay, NR ln V2 over V1. So I forgot the absolute value the first time I taught this class. Then it kind of flipped out. And I had no idea why the hell I was getting why I had a minus sign missing. And then I divided by this, nRT hot. Ln V2 over V1. Okay, gone. Okay. This is T hot minus T cold over T hot. And let me tell you that there's a really easy way to put this, which is on the exam, by the way. There's pencil rattling. T cold over T hot. Okay. And again, this is on your exam. Because I just wrote I wrote it last Friday. There you go. So that is the ultimate efficiency of anything that exists. And for various reasons that I don't think we'll get into today, actually I guess we will. Oh, this sucks. I hate this next part. Anyway, for a reason I'm about to get into. This is the best, most efficient engine that could ever be made to work ever. But it's not really that efficient. You know, it's finite. You can't ever, all right, let me draw the cycle again. And let's just analyze this before I do the next part. So I'll draw my 80 of that. I know this is a little small. Okay, so when it comes down to, the reason that an engine can never be perfectly efficient is because of this area. It's this area under the curve. It's this guy. It's a loss. It's a loss that was necessary to reciprocate, to have the engine a permanent wound-up spring. It had to be this way. The reason you get a net negative area is because the total area is this. There you go. There's your total net negative. Now, can you technically have a perfectly efficient engine? Huh? Again, let's go with the opposite answer. All right. Other than no, yes. You just have to do what with this? Yeah, that one of you got it right. You either have to make the engine impossibly hot, which you really kind of don't want to do. That would be wasteful, and your engine would melt. Or you have the tailpipe at 0 degrees. At 0 degrees K, not 0 degrees Celsius like today. All right, now, why is that? Now think about this. I have an ice jacket, and I'm in the tailpipe of my car. And it's at 0 degrees. But I have my nice jacket. I have a really nice jacket, a really thick jacket. So I can withstand 0 degrees. But there's something, so that won't kill me, but I'm going to die. All right, what's going to kill me? It's not the cold, it's the what? What else do I have to do? Drink, yes. Breathe. I have to breathe. How much air is in the tailpipe at 0K? None. It's liquefied, or it's solidified actually. It's solidified. There's no air. There's no pressure. There's no pressure inside of a tailpipe at 0 degrees. So that makes the area under the curve, it does this. Actually, it would go straight down. I never try to overwrite my own drawings. It flattens the bottom part. There's no work. There's no work to expand into a vacuum. When there's a vacuum here at 0K and there's no gas. No gas, there's nothing. It's just vacuum. You've already worked the problem on your homework. Expanding into a vacuum, requires no work whatsoever. So there's no loss. So that's how you build a perfectly efficient engine. Now, there's a lot of cool factoids about this. Not only is this, I think this is just kind of awesome. You guys don't care that much, do you? I think it's awesome. At least someone in here likes it. So, the reason I think this is really awesome is that, for one, it's an absolute fundamental about engines. And engines drive everything. Another cool thing, how high does an airplane fly? Why don't we just fly 10,000 feet? That'd actually be safer. You know why? You can breathe at 10,000 feet. Above 10,000 feet, not enough air. You'll die. So why don't we fly 10,000 feet? We fly at, anyone knows? Around 30 to 40,000 feet. We always fly at 30 to 40,000 feet. Why? It's cold, that's right. The air is very cold up there. If you look at it's like temperature versus altitude. I'm just doing this off the top of my head. You see this curve like this, and this is about 30 to 50,000 feet, roughly. And so that's why they do it. That's because the engines are more efficient. That's the only reason they fly that high. If it wasn't for that, they'd fly at 5,000, 10,000 feet, which would be infinitely safer, but they don't care. So, because they care more about the gasoline than they do you. Actually, that's horrible but true. So, anyway, I go kind of prattling on and on. And so I don't have much else to say about this other than this is what it is. With an infinitely cold engine, infinitely cold tailpipe, it kind of makes sense. And I don't have much else to say. Let me say that. One last bit that I have to go over. And, folks, this is really going to cross your eyes. This is really about my least favorite day because of all all of this, but what I want to do is do the total entropy. So how much entropy does this engine make? Because I can tell you that there is no such thing as generating negative entropy. That's impossible. It's just not how the universe was built. Maybe a different universe, but not this one. So what I want to do is sum up the entropy of the cycle and show you, well, as you're already guessing, it's going to be 0. Yes, it's going to be 0. And that's why this is the most efficient engine that exists. Because you can't possibly do better than generate 0 entropy. You can't suck entropy into a vacuum. You can only create it or do nothing. And so, anyway, yeah, anyway, total entropy. Okay, now this gives me a headache. I will almost always screw this up. So what I have to do is talk about the heat, the exchange of Q divided by the temperature. And so there was only 2 steps where there was a change of Q. There was Q1 plus Q3. And I hate doing this so much, I'm going to stop. And I'll get to it in a second here. We've still got 10 minutes of class. I can get through this. Now, you engineers, before I screw up the worst, T hot over T cold. Okay, chemists, this is something that engineers get right that we get terribly, terribly wrong. Okay, now you engineers, entropy is heat over temperature plus what? Yeah, plus the entropy generated. So here's the damnedest thing. Us chemists, we are dogmatic, and that is just exchange of heat over temperature. But engineers have an exchange of heat over temperature plus they actually put a question mark. You know, it's just something else. It turns out that that's absolutely correct. Because if sorry. There needs to be a total change in entropy, not entropy. Entropy itself is very complicated. Anyway, so it turns out that when you do adiabatic irreversible calculations, like on your present homework, which I know is a little pain in the ass, that's why I have a handout, it turns out that there is entropy generated in an adiabatic irreversible situation that causes it, whenever it is, to work the way it does. So anyway, I'm following the chemist tradition of being very dogmatic about just an exchange of heat divided by the temperature of said exchange. So I'm being very dogmatic. I'm not quite being an engineer, but this still works. This still works just fine. Let's see. Okay, how do I do this? Okay, so the change, because I got rid of the thing, let me write all this down again. NR T hot, ln V2 over V1, because I just erased it. And let's do the cold. And that's the work. It's cold. That is nRT cold. Sorry, my handwriting is not the best today. V4 over V3. Okay. Now, I've already proved, but V3 over V4, I just did this a second ago, and I got rid of it very stupidly. V3 over V4 is V2 over V1. Again, sorry for my handwriting. Okay, so this guy ends up being minus. What I'm going to do is I'm going to pick up a minus sign. And, ooh, God, this is awful. Sorry. It's offensive to my eyes. It burns. Anyway, okay, what I'm going to do is I'm going to pick up a minus sign, flip this, and add that. Behold. ln V2 over V1. Okay, so, there we go. Okay, so now I'm going to have to do, I got this guy. Oh God, sorry, what have I done? Cold, hot. Sorry about that. They just put it straight through in your notes. My screw up. I get this wrong every freaking time. In fact, I'm surprised I haven't screwed up worse than I have. Okay, now, here's the name of this thing that's gonna actually make things a little bit easier. Okay, again, I'm gonna do a different derivation and then go back to this. So I define these guys. These guys are those guys, whatever. Now I'm gonna point out at dividing the dividend. Hot over cold. So I'm dividing the two heats. Hot over cold. What I've got is nRT hot, right? LNBQ over V1. All right, I pray to God I hope that's correct. Okay, I got that right. Over T cold, that's minus NR T cold. LNB2 over V1. Okay, it's obvious how much stuff cancels. Here we go. That's something canceled. And that is minus T hot over T cold. Therefore, okay, so what I'm going to do is I'm going to bring this guy over here and this over there. So the change in hot heat, T cold, is equal to the cold heat, T hot. Okay. If this hasn't stuck any worse, let me plug that sucker into there. Okay, so that's going to be change in heat, cold, change in heat, cold, T hot, over T cold, over T hot. I know this is painful, just bear with me here. Okay, there we go. Right, so I've done 2 steps of algebra, that's not too painful. Okay, plus change in heat, cold, over T cold. Right. I forgot a minus sign, didn't I?
Yeah.
Yep, thank you. This has gone better than I've ever done this before, by the way, just to point that out. Okay, so I've got a minus sign there. And this is therefore equal to, oh God, did it again. Cold over T cold, plus the change in T cold, T cold, and that's E0. So, I get it? Good. We okay? Yeah, there you go. Okay, so it's 0.